So there is one problem that we need to address before we roll this out, before we go crazy doing confidence intervals. This problem is that every time you construct a 95% confidence interval, you're 95% confident of capturing the true mean difference, which means 5% of the time you don't, 5% of the time you miss it. Okay, the thing is, we got to do lots of these confidence intervals. We can compare mean 1 and mean 2, mean 1 and mean 3, mean 1 and mean 4, 2 and 3, 2 and 4, 3 and 4, 6 confidence intervals. And if we had more treatments, if we had, say, 10 treatments, we'd have 45 confidence intervals to construct. Each of those has a 5% chance of missing the right answer. So if there was no difference between means, if all the means are equal, and you're doing a whole bunch of confidence intervals which each accidentally get the wrong answer 5% of the time, there's actually a pretty decent chance that we're going to get something wrong and falsely declare a difference between groups if we just focus on this 95% confidence intervals. Okay, we can actually, these tests aren't independent because they involve common terms, but we could use independence arguments to put a bound, to put a bound on the worst case scenario here. What if, let's just stick with 6. Let's just stick with our 4. Let's stick with our 4 treatments, which gave us 6 pairwise combinations. If we did 6 independent tests and each of them had 5% chance of telling us the wrong answer, what's our overall chance of making an error? Well, so what's the probability of type 1 error? In 6 independent tests. Well, it's 1 minus the probability of no error. Which is 1 minus. At the 0.05 level, okay, if we're doing it at the 0.05 level, each of them has 0.95 chance of giving us the right answer. If they're independent, and there's 6 of them, we got 1 minus 0.95 to the power of 6. What's that equal to? It's about 0.265. We've got over a 1 in 4 chance now of accidentally saying 2 means different. If we had 10 groups, if we had 10 teaching techniques we were comparing instead of 4, 90%. We'd be highly likely. We'd be surprised if we didn't get something wrong. So this is a problem that we need to deal with. Anyone doing an ANOVA, when they get to looking at pairwise comparisons, they should correct for multiple testing. They should correct for the fact that they're not just doing one confidence interval or one test to see if 2 means are different. They're doing lots of them across all possible pairs. So why am I making a big deal about multiple testing? One of the roles of statistics is to give us a bit of a reality check, I guess, because people are really good at finding patterns. You eyeball some data, it's like, oh yeah, I can see something happening here. You talk to people, conversation at the pub about a football match. It's like, this team won because they did this, they did that, they did that. They got this player who's great. Often it's just a toss of a coin, really, who wins. People get lucky, but it's a well-known fact that humans, they're so good at finding patterns, they'll find patterns even when they aren't there. It's quite common for people to be quite confident saying, yeah, this is going on. Just come up with some explanation for something which is actually just random noise. And it's easy to experiment on. It's well documented that people find patterns in noise. So a key role of statistics is checking if it is a pattern or if it's noise. And we want to control, critically we want to control our false confidence. We want to control for false confidence. We don't want to be saying there's something going on when there's not. Now, you got 10 groups you're comparing. 90% of the time, if you use 95% confidence intervals or 0.05 significance level, 90% of the time, you're going to accidentally say things are different when they're not. So the method isn't doing its job. It's not doing its job, it's letting us have false confidence. We're supposed to be guarding against that. We're supposed to be using statistics to guard against this idea of just saying that there's a relationship, saying that there's something going on because we eyeballed it and thought we found a pattern. So multiple testing is guarding against false confidence. It's doing this key job of statistics, stopping us from going crazy, just saying this is related to this is related to this, because I reckon I see a pattern. Okay? Now, how we didn't do it, there's different ways to do it. Probably one of the better ones is to use Tukey's HSD, honestly significant differences. But we're not going to talk about that one in this course because we'll talk about something that's simpler to explain mathematically. Okay, the simplest way to do it is to use the Bonferroni inequality. The Bonferroni inequality says that the probability of something out of a bunch of separate events happening, so the union of them all, is less than the sum of the separate probabilities. So the probability of at least one false positive is less than or equal to the sum of the false positive rates across each of the separate tests. If you've got k tests at significance level alpha, then the probability of some sort of false positive is less than or equal to k times alpha. So if we want to control the overall rate, so that we've got to control the rate of false confidence, basically. So we want to make sure that there's only a 5% chance overall of accidentally saying something's different from something else. If you've got k comparisons, why not just use a significance level of alpha divided by k? Instead of using 95% confidence intervals, if you've got 3 comparisons you're making, why not use, take alpha divided by 3, that gives you 0.017, well, 0.016 repeater, and hence use a 98.3 repeater % confidence interval for each of your comparisons, so that overall you've only got a 5% chance of making a mistake. So alpha, so the idea of Bonferroni, the short version is use alpha on k as your pairwise significance level, where there are k pairwise comparisons. I'm using an uppercase K here. K is equal to k choose 2, the number of possible treatment means we could be comparing.